Hello everyone. Welcome to another episode of Deep Dive Knowledge Talk Day. Hello everyone, and welcome to our interview with the author of the scientific report on V-JEPA. Today, we'll be discussing the fundamental mechanism of V-JEPA and why it is considered a predictive model rather than a generative model. To start, could you please provide a brief overview of the purpose and methods used in your study?
Sure. In our study, we investigated the fundamental mechanism of V-JEPA, a recently developed video prediction model. V-JEPA stands for Video, Joint Prediction, and Alignment, and it is designed to predict missing regions of a video based on the visible region. The key innovation in V-JEPA is the use of a predictor network that learns to generate residues of the missing regions, which are then aligned with the visible regions to produce a complete video. We conducted a series of experiments to evaluate the performance of V-JEPA on various video prediction tasks. Our results show that V-JEPA outperforms existing state-of-the-art methods on a wide range of tasks, including action recognition, video captioning, and video generation. One of the key findings of our study is that V-JEPA is a predictive model rather than a generative model. This means that V-JEPA does not learn to generate new videos from scratch, but rather to predict the missing regions of a video based on the visible regions. This is in contrast to generative models, which learn to generate new data that is similar to the training data.
Thank you for that overview. Can you explain how the predictor network in V-JEPA generates residues of the missing regions? What specific techniques or algorithms are used in this process?
V-JEPA's prediction network generates residues of missing areas by employing a technique called masked image modeling. This technique involves concealing specific portions of the input video clip and training the network to predict the missing content. The network accomplishes this by analyzing the visible sections of the clip and leveraging its understanding of the video's temporal and spatial structure. The specific algorithm used in V-JEPA's masked image modeling is a transformer architecture. Transformers are neural networks that excel at processing sequential data, such as video sequences. In V-JEPA, the transformer encoder processes the visible parts of the video clip, capturing the context and relationships within the sequence. This encoded residue is then fed into the transformer decoder, which generates predictions for the masked regions. To enhance the prediction accuracy, V-JEPA employs a multi-masking strategy. This means that multiple masked versions of the input clip are created, each with different missing regions. The network is then trained to predict the missing content for all of these masked versions, allowing it to learn diverse residues and improve its generalization capability. Overall, V-JEPA's masked image modeling technique, combined with the transformer architecture and multi-masking strategy, enables the network to effectively generate residues for missing areas in video clips.
Thank you for clarifying the role of masked image modeling in V-JEPA. Can you elaborate on how the Joint Embedding Predictive Architecture, JEPA, is utilized within V-JEPA? What advantages does this architecture provide for video prediction?
Joint Embedding Prediction Architecture is a fundamental mechanism used within V-JEPA. Video Joint Embedding Prediction Architecture that enables the model to predict missing regions in a video clip. JEPA plays a crucial role in V-JEPA's ability to perform video prediction tasks effectively. Imagine a video clip as a sequence of frames, like a flipbook. Each frame is made up of tiny squares called patches, similar to the pixels in an image. V-JEPA uses JEPA to predict the missing patches in a video clip. Here's how JEPA works within V-JEPA. 1. Masking the video. V-JEPA randomly selects some patches in the video clip and hides them, creating a masked video. 2. Encoding the visible patches. V-JEPA uses an encoder network to process the visible patches in the masked video. This encoder network converts the visible patches into a sequence of numerical residues called embeddings. 3. Predicting the missing patches. V-JEPA then uses a predictor network to predict the embeddings for the missing patches based on the embeddings of the visible patches. The predictor network learns to fill in the missing information by understanding the context and relationships within the video. 4. Combining embeddings. V-JEPA combines the predicted embeddings with the embeddings of the visible patches to create a complete set of embeddings for the entire video clip. The key advantage of using JEPA in V-JEPA for video prediction is that it allows the model to learn the joint distribution of all the patches in a video clip. By predicting the missing patches based on the visible patches, V-JEPA captures the temporal and spatial relationships between the different parts of the video. This enables V-JEPA to generate realistic and coherent predictions for the missing regions, resulting in improved video prediction performance.
Thank you for explaining the role of the Joint Embedding Predictive Architecture, JEPA, in V-JEPA.ai. Can you provide insights into how V-JEPA leverages temporal information to enhance its video prediction capabilities?
V-JEPA leverages time information to enhance its video prediction capabilities through the incorporation of temporal masking and a temporal stride. Temporal masking involves randomly masking out specific time steps within a video clip during the pre-training process. This forces the model to learn to predict the masked frames based on the context of the unmasked frame, fostering an understanding of temporal relationships and dependencies. Additionally, V-JEPA employs a temporal stride, which controls the interval between consecutive sampled frames. By using a stride greater than 1, the model is trained to predict future frames that are temporally distant from the observed frame. This helps the model capture long-range temporal dependencies and enables it to make predictions over extended time horizons.
Thank you for explaining how V-JEPA utilizes temporal masking and stride to leverage temporal information. Can you further elaborate on the benefits of using a transformer encoder architecture in V-JEPA for video prediction?
V-JEPA uses a transformer encoder architecture for video prediction because it allows the model to capture long-range dependencies and relationships within the video data. Transformers are particularly well suited for processing sequential data, such as video, as they can attend to different parts of the sequence and learn the relationships between them. This enables V-JEPA to make accurate predictions about the masked regions of the video, even when they are far apart in the sequence. Additionally, transformers are known for their ability to handle complex relationships and patterns in data, making them a good choice for modeling the rich visual information in video.
Thank you for clarifying the advantages of using a transformer encoder architecture in V-JEPA. Can you provide more details on how V-JEPA incorporates contrastive learning as part of its training process?
V-JEPA employs a contrastive learning objective during its pre-training process. Contrastive learning is a technique used to train models by contrasting positive and negative pairs of data samples. In the context of V-JEPA, the positive pairs consist of the original video clip and its masked version, while the negative pairs are formed by randomly shuffling the temporal order of the frames in the video. During training, V-JEPA learns to project both the original and masked video clips into a common feature space, where the positive pairs are pulled closer together and the negative pairs are pushed further apart. This process encourages the model to learn residues that capture the underlying structure and relationships within the video data. The contrastive learning objective is crucial for V-JEPA's success in several ways. First, it helps the model to learn residues that are robust to noise and distortions, as it must be able to distinguish between the original and masked versions of the video clip. Second, the contrastive objective encourages the model to learn residues that are discriminative, as it must be able to differentiate between positive and negative pairs. Finally, the contrastive learning process helps to prevent the model from overfitting to the training data, as it is forced to learn residues that generalize well to new and unseen videos.
Thank you for explaining the incorporation of contrastive learning in V-JEPA's training process. Can you further elaborate on the specific data augmentation techniques utilized during V-JEPA's pre-training?
V-JEPA uses several data augmentation techniques during pre-training to enhance the model's robustness and generalization capabilities. These techniques include horizontal flip, Randomly flipping the video clip horizontally helps the model learn to recognize actions and objects regardless of their orientation. Random resize scale. Randomly resizing the video clip to a scale between 0.3 and 1 introduces variations in the input size, making the model more resilient to different image resolution. Random resize aspect ratio. Randomly resizing the video clip to an aspect ratio between 0.75 and 1.35 helps the model learn to handle videos with different shapes and proportion. Masking. V-JEPA also employs masking techniques to encourage the model to focus on specific regions of the video clip. Dead Tasiyana. Tassagens. Kai. Kanederasi. Lion Nol. Tenol Lei. Anentie. India. Inspire also employs masking. It applies block-shaped masks with random aspect ratios between 0.75 and 1.5, covering a certain percentage of the video frame. This forces the model to predict the masked regions based on the surrounding context. Short-range mask. The short-range mask is applied to consecutive blocks of the video clip, covering a spatial scale of 0.15. This helps the model learn local temporal dependencies within short segments of the video. Long-range mask. The long-range mask is applied to blocks of the video clip that are further apart, covering a spatial scale of 0.7. This encourages the model to capture long-term temporal relationships and dependencies across the entire video clip.
Thank you for providing insights into the data augmentation techniques used in V-JEPA's pre-training. Can you further explain the role of the multi-resolution training strategy in enhancing the model's performance?
The multi-resolution training strategy contributes to the enhanced performance of V-JEPA by enabling the model to learn from videos of varying resolutions. This strategy involves training the model on multiple resolutions of the same video clip, allowing it to capture diverse visual features and motion patterns. By exposing the model to different levels of detail, it can develop a comprehensive understanding of the video content. This multi-resolution approach helps V-JEPA generalize better to unseen videos and improve its performance on various downstream tasks.
Thank you for explaining the multi-resolution training strategy. Can you elaborate on how V-JEPA incorporates self-supervised learning techniques during its pre-training process?
Sure, I can explain that. V-JEPA employs a multi-masking strategy for self-supervised learning during pre-training. This strategy involves utilizing two distinct masks, known as short-range and long-range masks, to enhance the model's ability to predict masked regions in a video clip. The short-range mask focuses on local temporal and spatial dependencies within a small neighborhood of the masked region. It helps the model learn to predict masked regions based on their immediate surrounding. On the other hand, the long-range mask targets more distant temporal and spatial relationships. It encourages the model to establish connections between distant parts of the video clip, fostering an understanding of the global context. By combining the predictions from both short-range and long-range masks, V-JEPA gains a comprehensive understanding of the video clip, capturing both local and global patterns. This approach enhances the model's ability to make accurate predictions, even for occluded or missing regions in the video. Additionally, V-JEPA employs a multitask learning objective during pre-training. It involves predicting not only the masked regions, but also the depth of each pixel in the video clip. This depth prediction task helps the model learn to understand the 3D structure of the scene, further improving its ability to make accurate prediction. Overall, the combination of multi-masking and multitask learning in V-JEPA's self-supervised pre-training enables the model to develop a deep understanding of video content, laying the foundation for its strong performance on various downstream video understanding tasks.
Thank you for clarifying V-JEPA's self-supervised learning techniques. Can you further elaborate on the choice of contrastive learning objective in V-JEPA's pre-training process and its contribution to the model's performance?
V-JEPA uses a contrastive learning objective during its pre-training process. Contrastive learning aims to learn residues by distinguishing between positive and negative pairs of data samples. In V-JEPA, The positive pair consists of two views of the same video clip, while the negative pair consists of two views of different video clips. The contrastive learning objective encourages the model to learn residues that are discriminative, meaning that they can distinguish between different video clips. This is important for downstream tasks, such as video classification and action recognition, which require the model to be able to tell different videos apart. The choice of masking strategy is also important for the performance of V-JEPA. The random tube masking strategy, in which a random fraction of tubes, spatial patches extended across the entire temporal duration, is removed from the video, encourages the model to learn residues that are robust to occlusions and missing data. The causal multi-block masking strategy, in which the first P frames of the 16-frame video are masked with a random set of spatio-temporal blocks, encourages the model to learn residues that are temporally coherent. The multi-block masking strategy, in which a random set of spatio-temporal blocks is masked from the entire video, encourages the model to learn residues that are both spatially and temporally coherent. The ablation study on the size and quantity of masked spatio-temporal blocks shows that the performance of V-JEPA is not sensitive to the size of the masked blocks, but it is sensitive to the number of masked blocks. This suggests that the model is able to learn effective residues even when only a small number of blocks are masked.
Thank you all for joining us today. I hope you found this discussion as informative as I did. To recap, we've learned that V-JEPA is a cutting-edge approach for predicting missing regions in videos. It leverages advanced techniques such as predictive models, contrastive learning, and transformer architectures. V-JEPA's joint embedding approach captures both temporal and spatial relationships within videos. Its use of self-supervised learning enhances its understanding of video content. The choice of masking strategy, such as the causal multi-block masking strategy, plays a crucial role in the model's performance. This emphasizes the importance of carefully selecting and optimizing the masking strategy for video prediction tasks. Remember, V-JEPA's innovative techniques have the potential to revolutionize video processing and editing. We look forward to seeing the exciting advancements that stem from this research. Thank you again to our esteemed guests for sharing their insights. And to all of you, thank you for your participation.